So here I have the 200 M&Ms that I counted out earlier, and I'm only going to show one trial because if I did 10 trials on camera, that would be a really long time. So now I'm just going to count the number of M&Ms that are facing up, and those represent the non-decayed ones, and the M&Ms that are facing down. And I'm gonna keep the M&Ms facing up in the box, and I'm gonna continue until none of them are facing up and they've all decayed. So I just finished counting and calculating my experiment. I only got to 9 trials, but that's how long it took me for all of them to decay. And the percent activity was calculated by doing the number of non-decayed over 200, which is the total amount. And I guess technically the decayed M&Ms are supposed to add up. So like each time you add from the previous amount, but I just took the number I counted after each trial. So here's the graph I made, with the black line being the line of best curve and the red dots being the actual data plotted. And as you can see, it's an exponential decay as it curves down and all the way until 0, until it's completely decayed. And the questions, what fraction of the original amount would be remaining after 10 half-lives? I only got to 9 half-lives, so it didn't work out. So I calculated under perfect circumstances, approximately 0.098 of the original amount would be remaining if you keep halving it from the original. And short half-lives of radioisotopes would be used in medicine because you wouldn't want something radioactive in someone's body for a prolonged period of time, so as short as possible. And for number 3, to calculate, I got 9.38 grams remaining, and I just used this formula I learned from Honors Chem, and its amount remaining equals initial amount times 1/2 to the power of time elapsed divided by the time of the half-life. And these are my calculations. And for number 4, I just set up a proportion. So according to the thing, it said 1 half-life equals 30 days. And so and you're trying to find how many days 10 half-lives are, so you do 1 half-life over 30 days is equal to 10 half-lives over X amount of days. And I got 300 days elapsed. So for number 5, I calculated and I found that from September 1st, 2016 to June 1st, 2017 is 273 days, and I got 5. So it stopped recording, but for number 5, I ended up getting 5.22 grams remaining, and I just calculated with the same formula as before for number 5. For number 6, the relationship between percent activity and number of half-lives, like I said previously with the graph, an exponential relationship was shown because the percent activity is halved each time the number of half-lives is decreased by 1, and the graph shows a curved exponential decay. M&Ms are a particularly good model for radioisotopes in this activity because ideally a half-life is the amount of time it takes for the sample to decay. So since there's a 50-50 chance of the M&M landing face up or face down, approximately half will decay each half-life / trial. Some other everyday materials that could be used would be anything with 2 options or a 50% chance of occurring, such as Skittles, since they have the exact same design, and coins, which probably wouldn't be ideal because they're harder to obtain that many. And in conclusion, this lab demonstrated the half-life decay with M&Ms instead of radioisotopes. By calculating percent activity, it was evident as to how much of the original sample was decaying, and the percent was halved each trial. By graphing the percent activity versus the number of half-lives, the exponential relationship was established, since percent activity is halved each time as the half-life increases. Using M&Ms was a good way to help understand half-lives because, like half-lives, roughly half the M&Ms will decay every trial, since there's a 50% chance that the M&Ms may land later down. The math problems also helped solidify our understanding of half-lives by having to see them in number terms.